I've been asked to have a few words on what numerical simulation is. That wasn't a topic that I came up with. I was invited to speak on that. And I think it is a good topic. I think there are a lot of people in this room that are sort of vague on what that entails. And so I'm hoping to try to help at least some of you have a better idea, a better grasp of what's involved. And I've been involved with this field for, let's see, probably, well, coming up on 60 years. It's a long time. Okay. So why is numerical simulation even possible? Well, I think a simple answer is that it has been discovered, and to some extent astonishingly, that the material realm around us behaves according to a set of mathematical laws. And that discovery, something like 600 years ago, led to the advent of what we know as science. So that was a pretty significant discovery back in that era. And basically it's transformed the world. It's radically and continues to radically transform the world we live in. So what are some of the examples of these mathematical laws? Well, there's some simple examples I think most people can grasp. One is just the conservation of mass. That, apart from some nuclear reactions, generally the amount of physical mass does not change. And so, similarly for energy, that in most cases we can depend on in a model that the energy is going to be conserved. And then we have other laws like Newton's laws of motion. And so numerical simulation provides an approximate but accurate solution to extremely complex and difficult problems. So that is the rationale for numerical modeling. It builds upon the fact that there are mathematical laws that describe how nature behaves, and the simulation part of it means that we can probe things like what goes on inside of a star or inside of the Earth, or other very, very difficult problems. How to forecast the weather, how to build a rover to send to Mars, all kinds of things. And so these laws make it possible to describe the behavior of physical systems in terms of mathematical equations. And so like I said, it's transformed our world, this understanding. And so numerical simulation provides an approximate but accurate solutions to extremely complex and difficult problems. And I just gave some examples. And actually most manufactured products we use today involve some amount of numerical simulation in their design. And because the realism that can be achieved, numerical simulation today largely has replaced the building and testing of engineering prototypes. The simulation process is so good today, aided by the kind of computer power that we have today, that many systems you really don't even need to build an engineering prototype. You can design it, check your design, and then build it and rely on it working. And so that's quite an achievement. So another question, where does a person acquire the training to do numerical simulation? Well, most undergraduate programs in mechanical and civil engineering today, for example, provide the essential mathematics and physical background needed, as well as training in computer programming and basic numerical methods that can be used to solve large systems of equations that these simulations entail. So basically, that's what engineers do. You know, so if a person wants to be able to do numerical simulation, you know, complete an engineering program, and you'll likely be fairly well equipped to do that. There are other fields today, especially fields of science, where that same kind of training is available in many programs. And at the graduate level, it's common even in more programs than you normally would see at the undergraduate level. So most of these programs also provide training opportunities on commercial simulation software packages, especially in engineering. So today, many engineers are trained to use some extremely sophisticated simulation packages, commercial simulation packages. Whereas back in my day, and I think it was, well, it played a role in my history, we were taught how to write the packages themselves, how to write the software to do the simulations directly. Okay. So what does a numerical simulation entail? Well, I've got 5 steps here that I would point to. First is a physical description of the system. And I'll give an example, but you've got to first have a good physical description of the system you want to simulate. All right, then the second step is a mathematical description of that system, of that physical system in terms of the laws of physics. In other words, equations expressing those laws and identifying the appropriate variables that you're going to use, that you need to, that the equations, that the mathematical laws entail. Okay, and then the next step, once you've got the equations, once you've identified the mathematical laws, have the equations that those laws imply, then you need some sort of numerical approximation or representation of those equations, usually on a computational grid of some sort. If it's some kind of physical system, you're going to represent it on a grid, and you need to represent those equations in some kind of numerical manner that's appropriate for that grid. All right, the next step is a computer code that translates that numerical approximation into a language that the computer can process. And finally, the final step is the simulation itself, and it's these days, because computers are so capable, use it often on a large computer, but you also need the visualization and the analysis of the results. And in most cases, you've got so many, the simulation is so complex, there's no way to understand the results other than graphically. So this visualization step is crucial today in simulation. There's no way, and typically when I myself run a big simulation, it may take me longer to visualize it, to look at various variables, look at, you know, and I may spend way more time visualizing it than I did running it. So often as far as the progress in this kind of work is concerned, the time limiting step is the human being able to understand what the simulation is saying. It can be a very intensive kind of a thing to try to understand what that simulation is saying. And sometimes I'll have to admit I have missed. I've looked, I looked over the results. They were more or less what I expected, but I later realized I overlooked some very significant details that I just wasn't expecting, wasn't paying attention to. So that step of analysis at the end is very important. So before we look into more details on what I just said, let's consider an example of a numerical simulation. I've chosen one I played a role in as a staff member in a computational fluid dynamics group at Los Alamos National Laboratory some 20 years ago. This example is a code that was named as POP for Parallel Ocean Program. It used to simulate the Earth's oceans. And we had a competing code that was named MOM for Modular Ocean Model. And so we decided to name ours POP. Anyway, and this POP code was a component of a larger global climate model managed by the National Center for Atmospheric Research in Boulder, Colorado. It was one of the two main climate models, back 20 years ago, used in the country. This simulation used a computational grid with 177 million cells, chopping up the global ocean into that many little blocks, and it was designed to execute on in a parallel manner on multiple cores of a large supercomputer. Okay, so I'm just going to give you a few little snapshots and then some videos. These are just some stills here, some snapshots of the ocean surface temperature just below the surface, 15 meters deep. For this code, we had a resolution of about 10 kilometers. So we had a grid point about every 6 miles in the grid over the world ocean. So you see the example, some of the detail of the Gulf Stream. Here the color denotes temperature. So you see the warm temperatures along the east coast and crossing the Atlantic. Then we have down the east coast of Africa, what's known as the Agulhas Current, coming around the tip of Africa. On the east side of Australia, the East Australian Current, and then in the Pacific, off the coast of Japan, the Kuroshio Current. So this model was able to successfully capture some of these main currents in the ocean. This is a little animation. You can see the Agulhas Current coming around the tip of Africa because the water has such low viscosity. There's turbulence, and you see these turbulent eddies spinning off, coming out into the South Atlantic from the current. And down at the very bottom, I'll show another animation here, but you have the circumantarctic current going from west to east, the opposite direction. Okay, and so this is showing that current, the Antarctic circumpolar current, and the eddies that it produces. And this is another part of the code. This is from the North Pole, showing the Antarctic, the currents in the Antarctic. I'm sorry, in the Arctic. All right, and here's another simulation. In this case, the colors denote temperature, and you see the let's see. You can see the shift from winter to summer. That's the temperatures getting warmer and cooler. Okay, so that's and so these are this is a map of some of the main currents, and we're capturing quite a few of them in this model. So what did this simulation entail? Just how did we accomplish the several steps I just mentioned? Well, the physical description of the system, the material is salty water. We need the bottom topography of the ocean basins. So we had a numerical database providing that. We needed a description of the surface winds through the course of the year, everywhere on Earth. We needed air temperatures. We needed the solar input. And so these boundary conditions were, had to be averaged, of course, but that was part of the input for the problem. We accounted for the fact that the Earth, the ocean is on a rotating Earth, so we had to fold in the Earth's rotation and, of course, gravitation, account for the Earth's gravitation in the problem. And so what did the numerical simulation involve? Well, the equations that we used expressed conservation of mass, energy, and momentum. These equations express, in other words, they include Newton's laws of motion. We include forces that describe the effect of gravity and the Earth's rotation. And some of the variables in those equations include water velocity, temperature, salinity, and surface height. So we identify. So this gives you. I'm not giving you the actual equations, but you get a flavor of the kind of equations that we used in the model. And so this is the on the left is the grid that we used. It was a latitude-longitude grid, but we displaced the North Pole such that the North Pole was above land in Canada. So we're able to include the entire global ocean in this grid, and nevertheless use a more or less regular latitude-longitude grid, where we cut out the regions right near the pole where the cells become so small. Otherwise, the cells, and it had 40 layers of cells vertically. They're basically little cubes. So it's relatively straightforward to solve conservation equations on cells like that, where if there's no, you conserve mass, so the mass coming in all 6 sides of the cube, the net flow has to be 0. And anyway, it's relatively, I'm trying to avoid a lot of equations, but straightforward to express those equations in numerical form on the grid. And then I mentioned the computer code, and I had to look a little bit to find some code that was simple enough that I might. But this shows, in those days, we were writing our code in Fortran, and this is an example of some Fortran code that basically computes the direction of the Coriolis vector. Very simple, and just uses some trigonometric functions, sine and cosine, and so it computes. It involves some variables like some variables describing the rotation axis. Omega is the rotation speed of the Earth, and then this next to the last line is the calculation of that vector. The colon there denotes it's over all the grid points in the grid. Or it's in one layer. I'm sorry. Anyway, you then need. My point is, you need to write those equations, the numerical form of the equations in terms of computer language, computer code. All right, And then the next step is running the simulation and visualizing it. Okay, and then analyzing the results. So again, I've just illustrated these 5 steps I mentioned earlier. All right, where did I gain the expertise to do numerical simulation? Well, I obtained a bachelor's and master's degree in electrical engineering that included an introduction to numerical methods and the ability to program in Fortran. And that was basically in the late 1960s. I served 4 years in the early 70s as an Air Force officer at the Air Force Weapons Lab, where I participated in the design of the laser for the Airborne Laser Laboratory, which was a highly classified project during Vietnam time. We put a large laser in a refitted KC-135, and that program was highly successful. The objective was to demonstrate that we could shoot down missiles with lasers from an aircraft. And a pretty ambitious kind of program, but its success enabled President Reagan in the early 1980s to get his Star Wars program, a much bigger program, his Star Wars program, approved through Congress. So anyway, that's how I got some of my, and as part of my work in that program, I developed a 3D model for extracting laser power out of the laser device. And so I got some key experience in writing code, building a numerical model. Okay, and then a little more of my background. I have a lot of text here. You don't need to read it all, but after my tour of duty, my 4 years in the Air Force, I joined Campus Crusade for Christ as a campus staff member. Creation apologetics prompted me in the spring of 1978 to investigate how observations supporting plate tectonics might shed light on the Genesis flood. And as I looked into that, I realized that all of today's igneous ocean floor had cooled and solidified since all the Paleozoic fossils had been buried. That meant that the flood logically had to have been a tectonic cataclysm. And at that point in the creation literature, I saw that I couldn't find anyone else who had come to that conclusion. I realized this was really significant as far as defending the flood. And I prayed about it, and I ended up a few months later decided to leave Campus Crusade and to enroll in a PhD program in geophysics at UCLA. A pretty big step of faith for me at that point, but then I wasn't there very long until there was plenty of confirmation that God indeed had called me to that. And so then at UCLA, God opened some incredible doors, including the opportunity to undertake my dissertation research at Los Alamos National Laboratory and to collaborate with a mathematician there named Paul Fredrickson, who had recently discovered a powerful new computational method known as multigrid. And working closely with Paul, in just a few months' time, together we wrote the 3D spherical geometry program now known as TERRA for simulating flow of rock inside a planet like the Earth. So God directed. It was a thrilling ride. But basically, God handed me my PhD on a silver platter, and I was, hardly could believe all this unfolded. And the efficiency of that method that Paul Fredrickson had discovered, combined with the power of the supercomputers at Los Alamos, enabled me to build the first 3D planetary mantle dynamics program in the world, and which amazed my PhD committee. They were very happy to give me a PhD. It brought them a lot of credit. Have somebody like that at their school to develop that first code like that. And Los Alamos also was looking for PhDs with this kind of skill. And so they made me an offer that I just couldn't decline. First of all, the benefit of working in their premier computational fluid dynamics group, plus as part of the offer that I could work part-time on my own research. And the guys that hired me knew that my model, I was seeking to model a flood. So they were knowledgeable by that, and nevertheless offered me that position with that kind of benefit. So I saw that very much from the hand of God. There's no doubt about that. And it's just most of you probably have never been there. It's up in the mountains, Los Alamos in northern New Mexico. It was designed during World War II to be a place where the activity there of developing the first atomic bomb could be kept secret. And so it's somewhat in a remote place, but a very beautiful place. When I was there were about 7,000 PhD scientists. Many of these people were top specialists in their fields in the world. And the lab had the latest and fastest supercomputers. And I spent 20 years there in computational fluid dynamics research and retired back in 2004. But it was an incredibly stimulating place to work, and it was during that time that I was able to put together much of the evidence put together a computational model that gave a lot of clarification about catastrophic plate tectonics. So let me give you a little more description of that code that I put together for my PhD thesis. Now, I apologize for some of the terminology here. It's the method, the particular type of formulation. It's known as finite elements, and in that formulation, the variables are modeled as piecewise linear. In other words, instead of varying smoothly as in a continuous way, I'm approximating the functions as piecewise linear from one grid point to the next. And if your grid is fine enough, that's a good approximation. The grid is it's a special grid that Dr. Fredrickson and I he recommended based on the regular icosahedron. I'll talk about that in a moment. The code exploits the power of the multigrid method to solve these equations with just unbelievable efficiency. And the regular block data structure that's inherent to that grid was naturally suited for splitting the grid up into multiple little blocks and processing these on a parallel computer. So it was designed for very efficient execution from a computational standpoint, and we had built in was the flexibility to treat very realistic conditions in the Earth: compressible flow, spatially varying material properties, realistic equations of state, and lithospheric plates. Okay, this is a cutaway view of the grid, computational grid. There's a slice cut out of it so you can see what it's like in the interior. This is a relatively low resolution version of that grid with 32 radial layers and in total 1.3 million cells. And it solves the equations of conservation of mass, conservation of energy, and a balance of forces in each cell on each time step. And just to give you a glimpse of how the grid was constructed, we projected what is known as the regular icosahedron. That's one of the platonic solids with 20 facets, 20 triangular faces. Project that on the sphere, divide the sphere into 20 equal spherical triangles. You can get a finer grid by connecting the midpoints of the sides of those triangles with great circle arcs. and then just repeating that process to get as fine a grid as you might want, and then replicating that grid in the radial direction to fill in the interior to get a spherical shell. This is a grid that we used through the 90s, and even I can run this grid now on my laptop. It's got 10 million cells. Okay, and here are the equations that TERRA solves, and I was almost didn't put the slide in, but because it's expressed, the equations are expressed very compactly in what's known as tensor calculus notation. But the top equation just simply represents a force balance on each cell involving the pressure gradient. There's a force, if pressure is changing, there's a force. That force is accounted for. There's a force if a blob of material is heavier than what its surroundings are, there's a buoyancy force. That's the middle term. And then the last term has to do with the deformation force of the material itself, of the rock itself. And the second equation is simply a description of the conservation of mass. And the next equation is the conservation of energy. And then this next fourth line is a description of the deformation, how the deformation is related to the velocity field, and so on. So those are the equations that TERRA solves. So I'm going to give you an example of that calculation. Of course, that grid is intended to model the mantle of the Earth, the region between the core and the Earth's surface. And so it has the ability to track plates on the surface. This particular simulation starts with a representation of Pangaea with the continents all together. You see the representation of the continents in black here, my version of Pangaea. And to get the calculation going, you needed some kind of little perturbation to get the rock moving, and I put zones of coal rock around much of the perimeter of Pangaea, plus a strip running down toward Australia, and so that rock was 400 degrees colder than the surrounding rock, and went down to a depth of 400 kilometers down into the Earth. So relatively small perturbation. That's what it looks like in cross section. The 400 kilometers into the Earth, 400 degrees colder, and then I just let it go. And so the solving those equations, the sinking material around the perimeter of Pangaea tends to pull that supercontinent apart and cause seafloor spreading in the places you see there, and so that's that. I'll just play that again, I guess. So you see the blocks moving basically in the direction that we know from the seafloor today, the way the continents moved. This is a cross section through the Earth. You see the cold material sinking and settling down onto the core mantle boundary. Here, temperature represents, our color denotes temperature, blue cold and red hot. This is a view from the North Pole, the continents moving, and another view from the South Pole. So a long-standing physics issue in terms of the flood and in terms of catastrophic plate tectonics, how can ocean plates sink vertically through 2,900 kilometers or 1,800 miles of solid rock, solid mantle rock, in a few weeks' time? And when I developed the code, the answer had already been available for some, well, relative to today, some 50 years in laboratory experiments on silicate rocks. And I won't go into detail, but this is an example of an apparatus for measuring the deformation properties of mantle minerals. The cylinder is an oven for controlling the temperature very carefully. Stress is applied through silica rods from the top and bottom, and the sample is in the middle of the cylinder. And so you can heat the sample, apply stress to the sample, and then after the sample is deformed, take it out, look at it under electron microscope, and in some cases you see where planes of atoms have slid over one another like shearing a deck of cards, how the cards slide past one another. So how silicates deform has been something that has been studied by geophysicists for several decades. And even back, this is a review paper from 1983, even by 1983 there was enough data from these experiments to map the deformation behavior. I don't expect you to have any idea what this graph is saying, but basically it shows that, I can just assure you that it shows you that this silicate mineral olivine, which is the dominant mineral in the Earth's upper mantle, can deform by a factor of 1 billion at the temperatures, at temperatures that exist in the mantle and plausible amounts of stress that can occur in the mantle. These experiments show that the mantle can become dramatically weaker than it is today by many orders of magnitude, factor on the order of 1 billion. And basically what that means is that catastrophic mantle overturn is a genuine possibility for the Earth. And so I realized this pretty early on in my studies. But I had encountered a big problem, because even with this new numerical method I had, my code wasn't robust enough to handle a genuine physical instability. So it wasn't until the late 90s that we were able to crack that problem. And it was through a PhD student, a graduate student at the University of Illinois, a Korean guy, Woo-Sun Yang, as part of his PhD thesis, found a way for improving the basic multigrid method. Am I out of time? Okay. Okay. All right, I'll just go through my slides. Anyway, he cracked that problem. We found that basically the mantle, when runaway begins, the weakness propagates throughout the mantle. The blue here represents weakness. The mantle is 1 billion times weaker in this dark blue region on the bottom. That's viscosity on the bottom. So it gave a lot of clarity for how this runaway mechanism worked. And so I've done it more recently in cylindrical geometry. The same thing applies, and same thing, same weakening by a factor of 1 million. Blue is 1 billion times weaker than it is today. All right, so we're working on that to do it in 3D, and I'm later in the week going to talk about how tsunamis that this process of catastrophic plate tectonics generates is capable of producing the flood sediment record, something like 6,000 feet on average of fossil-bearing sediment on the continents. That amount of sediment can be produced within the few months of the flood by these large tsunamis. So this is a simulation, again using numerical modeling to simulate the tsunamis that the catastrophic plate tectonics produces, and erodes the edge of the continents, produces a tremendous volume of sediment that gets carried and deposited on the continents, producing the sediment layers that we see today. So my talk's scheduled for 10 o'clock on Wednesday. where I'll be talking about this model. You see the continents breaking apart here, and as that progressive. So in summary, numerical simulation is a powerful tool for investigating the natural world that God has created, also for unraveling his mighty interventions in the past, for example, during the flood. So I thank you for your attention.